Okay, we've been talking about here chapter 14. Uh, and chapter 14 is our last organic chapter. And we got into, I believe, in this chapter, everybody that's left over, but really carboxylic acids we talked about. And remember that the functional group of a carboxylic acid is the carbon-oxygen double bond, the carbonyl-carbon, and the OH group there. And again, sometimes in formula written as like COOH. This is, as we talked about, a really polar group. It's got two polar parts. It's got the carbonyl-carbon, which is our double-bonded oxygen. That is positive and negative, where the carbon is more positive, the oxygen is more negative. And we also got our polar OH group happening there. So quite polar, this guy. We talked about previously and a number of times how we actually can make a carboxylic acid. Once again, a carboxylic acid is made through really, if we go way, way back, honestly, it is like you can start with the hydration of an alkene, which will give you an alcohol. And that'll give you a primary alcohol. And if you oxidize that primary alcohol, as we talked about a number of times, we will lose our hydrogen, and that will get you to your aldehyde, which will make a double bond. And lastly, if we then oxidize our aldehyde, that will get us to our carboxylic acid. So I'll just draw it down here. And remember, on this last sort of oxidation step, that's really where we're inserting the oxygen in there to make our carboxylic acid. So that is like way back when. Yes, that's all back into where it can all begin from an alkene, right? This is, as we've named all these guys, ethene. This is ethanol. This is ethanal, AL. And this is ethanoic acid, which is how we go about naming our carboxylic acids. You could go back to the alkane name and basically drop the E and put OIC acid at the end of it. A couple of reminders, much like the aldehyde, the carboxylic acid group there will always be at the end because of the hydrogen that's at the end. So because of this hydrogen that is here, that group should always be at the end. So a little bit different than some of the other organic groups, we do not need to give the location of where the carbon-oxygen double bond is located because it always has to be at one end or the other. But for numbering purposes, that is where you should start numbering the carbon chain, as that should take the priority. So that will always be carbon number 1 if there happens to be, again, other things attached to it. So again, if we had something like a chlorine there, for example, and we had this deal here, and maybe some extra hydrogens there would be good. We would have 1, 2, 3 carbons. So that will be propanoic acid. Again, this should be carbon 1, that should be carbon 2, and that should be carbon 3, which means this would be 3-chloral propanoic acid. So don't have to give the number for the carbon-oxygen double bond or that carbonyl-carbon there. But it should always be carbon number 1, whichever side of the molecule is located on. That is where you should start numbering, and that is how you will get the numbers for any other group that is basically attached. Any questions on any of that there? All right, so I think we did some naming and drawing of some of these to finish up last time. So let's talk about then some properties more officially here of carboxylic acids. Carboxylate salts are often used as preservatives, which is sort of what you get when a carboxylic acid sort of reacts. But because they really do have that very polar group on it, those two polar groups really, they do are very polar. They're also very soluble in water, and they're also going to have very high boiling points because of the ability to hydrogen bond with itself. So once again, unlike alcohols, which up until this point kind of were your champ there in terms of boiling point and sort of solubility, carboxylic acids, because of these two groups, definitely will beat it in terms of boiling point. So we have this group here, which works really well with water, and this group here actually works well with water. Although that second group there cannot hydrogen bond itself, it can participate in hydrogen bonding with, like a hydrogen from, say, water or something like that. So because of that, they definitely will form hydrogen bonds with water. With 1 to 5 carbon atoms, they are very soluble. So much like a lot of organic compounds that we've talked about, we do start to see a decrease in solubility once you build up the sort of non-polar side. So even with carboxylic acids, which have a pretty fairly polar spot here at the end, as you build up this non-polar side, once again, as we talked about in a number of cases, it gets a little bit too big. It doesn't allow water and everything to sort of work good together, as there's just that small part at the end there that's polar. So it gets to start to drop a lot in terms of solubility. So that's what we see as a number of carbons increase, we start to see the solubility decrease. Once again, as you can see in this picture, which is right here, that carbon oxygen double bond or carbonyl carbon, because it's positive and negative, that part can interact with water. And once again, oxygen is more negative and hydrogen is more positive. So it can again hydrogen bond through the carbon oxygen double bond, where the oxygen there is being supplied and the hydrogen is coming from water. It could also hydrogen bond, as you can see on the other end, where this is negative and this is positive, and so forth. So it could also do hydrogen bonding there. So that's why guys with less than 5 are quite soluble in water because of that. Acetic acid, which is ethanoic acid, is soluble in water. And that's vinegar, basically. And that's why it works well with water. Question on that. So here's our list. And again, right around after 5, we start to see that decrease in solubility. Benzoic acid, which is basically our benzene ring, that is a carboxylic acid, is slightly soluble. A reminder that when we talk about things being sort of slightly soluble, usually that leans more towards it being insoluble than soluble. But it is what the name implies. Slightly soluble means anything, actually, a little bit of it will dissolve. But slightly soluble is really more so like being insoluble at that point, which means it would not dissolve. Because they are also carboxylic acids, they can do really an acid-base reaction, just like a typical Bronsted-Lowry definition of an acid and base. So in this case, if we take carboxylic acid here, which is our ethanoic acid, our acetic acid, our vinegar, basically, this will act as an acid, obviously. Our water here will act as our Bronsted base. Which means he's going to basically send its hydrogen over to the water. The result of that is, if you remember when we talked about acid-base reactions, I hope so, we just took a quiz, but acid plus a base will give you a salt and water, is essentially what you form. If you remember, the water comes from the H plus from the acid, the OH minus from the base is basically how we get that water. Kind of the same reaction here. What we're left with is what's known as a carboxylic acid salt here. And that is basically the guy that lost the H plus. Because he lost the H plus, he will become one more negative, kind of like we talked about Bronsted-Lowry acid base pairs. When you lose that H plus, again, the charge changes. And then obviously we have our H3O plus here. So this would be our base and our conjugate acid, basically. And that would be our acid. and our conjugate base, just like in the Bronsted-Lowry definition. So carboxylic acids pretty much behave like acids, surprisingly enough. And we have that sort of same reaction that happens. So write the balanced chemical equation for dissociation of butanoic acid and water to identify the carboxylic acid salt. You don't have to worry about identifying the name of the salt or anything like that. But start with butanoic acid and draw what you should get when it reacts with water. So why don't you draw what you should get when those two. So we'll start with this. We'll work backwards. So oic acid tells us the carboxylic acid. Butane basically tells us it's 4 carbons. So that is where we will start with. Remember, it's got to have the carboxylic acid group there. So you can put it on one end or the other. We could finish out our butanoic acid by putting in our hydrogens in this case. So obviously this is an acid going to react with water here, which is really, in this case, if we just saw, going to be our base. So basically it's just going to donate its H+. This is the only H that could come off in that case. All the other H's are non-polar. So this is the only polar OH group there that's necessary for that hydrogen to come off and act as an acid. So that is the only one that should come off and send it over. Once again, because that's the only thing that changes, that's pretty much the only thing we're going to take out of our picture. Everything else will remain the same. And once again, because it did lose an H+, it becomes one more negative. So it was neutral to begin with. So now it'll become -1 in this case. And then obviously we'll get our hydronium ion H3O+ here as it accepts the H+ there from water, R2 water. Any question on that one there? By the way, we were talking about a second ago properties and solubility of carboxylic acids. Another one, as I mentioned a number of times, is again, carboxylic acids is one of the few organic guys that could beat alcohols in terms of boiling point. And that is because when a carboxylic acid gets together with itself, because of those polar groups, I'll do it like this, I think. They could actually hydrogen bond with each other like so and make what is referred to sometimes as a dimer. So instead of like an alcohol, it only has an OH group that could hydrogen bond once with itself. Every carboxylic acid could actually hydrogen bond with itself twice. And that makes for a much stronger association between the same carboxylic acid. And that relates to a much higher boiling point because they're able to do that hydrogen bonding like so here, for example, and here, and makes what is sometimes referred to as a dimer. And again, that's double association within 2 carboxylic acids. Again, it's going to make it twice as hard to break apart, and that will relate to a higher boiling point, which is why we see that in carboxylic acids. Alcohols, when they hydrogen bond with themselves, can frankly only really hydrogen bond in one place. So for every carboxylic acid, it can get twice the hydrogen bonding between molecules, and again, makes it much, much stronger together. Any questions on that there? And that's again why it could kind of be an alcohol in terms of boiling point. All right. Carboxylic acid salts are formed here, and that's the product, again, a salt and water. We're not going to really name the salts, so you don't have to worry about naming the salts, but you do need to be able to draw it. So once again here, we have our H and our OH coming together. When we take a acid here, and sodium hydroxide is a strong base. So once again, those two right there are going to make our water. And obviously what is left is this guy exactly the same as what you see over here, except now it has a negative charge because again, it lost the H+, and it will associate with that sodium, and that's what makes it a salt. So a salt's really just an ion on a compound. In this case, because it has the sodium, that's sodium methanoate. that's what makes it really a salt and water. So sometimes referred to as a carboxylic acid. Salt is formed as a result of a reaction of a carboxylic acid with really water or a base in this case. Any questions on that there? All right, so like I said, we're not going to name the salts, so you don't have to worry about that. So we'll kind of skip that part there. Carboxylic acid salts, though, they are solids at room temperatures. They have high melting points and are usually soluble in water because even though they have lost that hydrogen, they're now more ionic, so which makes them work well with water because they have that negative charge at the end, and they can still hydrogen bond through the carbon-oxygen double bond. So still has that solubility with water, even though it lost an H plus in the process. As I mentioned before, again, used in a lot of things as preservatives and flavor enhancers. And there's some of them there, sodium propanoate, monosodium glutamate, MSG, sodium benzoate as well. All right, so if we look at this propanoic acid, that's going to be 3 carbons. And oic acid tells us it definitely is our carboxylic acid. And in this case, we're going to react it with sodium hydroxide. So you can think of these again as very much like our acid-base reactions. So we know we need to get water, and we're going to take water the same way that we did when we did the acid-base chapter, H from the acid, OH again from the base, and that is going to make our water. Right up there. What is left is basically you're just going to kind of put these guys together, and that's going to make our salt, and nothing else will change. Except I should have a 3 there. There we go. That would be good. And we will have our sodium. So again, that would be our carboxylic acid salt in this case. Again, in terms of the carboxylic acid, all we did is take the hydrogen off and it becomes negative, going to be attracted to the sodium that came from sodium hydroxide. And again, that makes a salt very similar to like sodium chloride you would get when you take hydrochloric acid and sodium hydroxide together. You get sodium chloride as your salt. Any question on that reaction there? All right, that's what it shows, I think. Perfect. Carboxylic acid is also part of the metabolic process for our cells. So during glycolysis, molecules are broken down into pyruvate, and then you got pyruvic acid. As you can see, there's our carboxylic acid part, lactic acid as well, also carboxylic acid. So again, these are used by our cells as well through glycolysis, where we basically store sugar and break down sugar and use it for energy along the way. All right. Also, the Krebs cycle, citric acid cycle, a lot of, as we also will see, amino acids later on in the protein chapter are also carboxylic acids. And there is our carboxylic acid and our citric acid. And there we go. All right. The next sort of organic group we're going to talk about are esters. Esters have the functional group of carbon-oxygen double bond, oxygen and carbon. So very similar to a carboxylic acid, except no H here. It's a carbon group that's attached there. So that is your functional group for an ester. So really a ester is made really by taking a carboxylic acid, which is why it kind of looks like that, and also an alcohol and basically putting them together. So you take a carboxylic acid and alcohol, you will get an ester. Esters are things to smell. and they're responsible for smells and certain flavors and stuff like that. Some of what I think you'll do this week, you'll crack things together and try not to breathe too deeply and waft it towards you to get the smell of some different things along the way. So how do we make esters? They are a reaction of a carboxylic acid and alcohol. So how does that come together? If we take just the functional group here, we take our carboxylic acid and we react it with an alcohol. I'll just put that part right there. I'll just make a nice simple one here. So in this particular case, what happens is we take out water. H2O goes out. And we take out the water from the OH there from the carboxylic acid and the H from the alcohol. And we get our water that forms. And then what happens in this case is pretty simple. You just squeeze together what's left. So you basically start on the left here and you keep drawing what's there to the right. The only thing you shouldn't draw is what's in the box there. Take out the water and then basically just squeeze them together. So what we're left with in this case would be our CH3, our C double bonded O. That's the water that comes next. So there's our O, which gives us our ester connection. And right there is basically our ester connection that happens in this case. About there. So a ester is really a combination of a carboxylic acid and an alcohol. And as we'll see shortly, that is how we go about naming these guys. It's based on the alcohol and the carboxylic acid that it comes from. It is found in fats and oils. Again, it's responsible for a lot of aromas like bananas, oranges, strawberries, oil of wintergreen. Here is our ester right there. Here's how it looks in line formula. It's like that. When we draw it. And again, that is our carbon at the end, which gives us our carbon, oxygen, carbon with our carbon, oxygen double bond, which is necessary there for our ester group. This reaction that I just showed you was referred to as an esterification reaction. The esterification reaction is basically making an ester through reacting an alcohol and a carboxylic acid and removing water. So esterification reaction goes in this direction. As we'll talk about hydrolysis reaction, where you break it back apart, goes in the opposite direction. But once again, this is the one we just did. We have our ethanoic acid. We're going to take out the water. And again, we're really just going to squeeze together what is left over at that point. So this and this come together to make this and this. So you basically just kind of squish everybody together. Once again, you do not change anything else other than take out the water. So don't get fancy with it. Just take out the water and squeeze it together, and you have your esterification reaction that happens. So how do we go about naming this? As you can see down there, what we made in terms of our esters was known as methyl ethanoate. So when we look at this ester, as I mentioned before, there's really two parts to it. And where you should sort of think about it in terms of the naming aspect of it is kind of how you put it together. So where we take the water out and then we kind of slide them both together. That is where you should think about it in terms of how you go about naming it, which means if I were to look at this ester, I would draw me a line right about there. And heading towards the single bonded oxygen, there's basically two oxygens. There's one that is double bonded up on top, and there's one that is single bonded to the right in this particular case, but heading towards the single bonded oxygen and past it, away from the double bonded oxygen. That is going to be your alcohol part. Heading towards the double bonded oxygen and away from the single bonded oxygen. That's going to be your carboxylic acid part. So how do we go about naming it? Well, we go with the alcohol part and we name it as a group, as an alkyl group, right? And a 1-carbon alkyl group is known as a methyl, right? So that is where the methyl part of the name comes from. It comes from the alcohol part. The other part, I'll tell you, you can do it 2 ways, whichever way you like to do it. I personally remember it by the number of carbons, which is 2 in this case, which is ethane. And I drop the E off of ethane and I put O8 at the end of it. Some people will tell you to drop the IC acid part of the carboxylic acid name. So drop the IC and the acid and just put 8 at the end of it. So whichever way you want to remember it, you could do that. So that is 2 carbons, which is based off of ethane, and just drop that E and that becomes ethanoate. And then you just put it together with the group coming first. And that would get us how we get down here. Our methyl ethanoate would be this proper name. So there's kind of 2 parts to the naming of an ester. One part is named like an alkyl group, and that should be the part that always comes from the alcohol. And that should be, frankly, attached to the single bonded oxygen, away from the double bonded oxygen. And the other part basically is the carboxylic acid part, which is basically, again, however you want to do it, either to drop the IC and put 8 at the end of it, or go all the way back to the alkane, drop the E and put O8 at the end of it. And that is basically how you get the base of the name. Any questions on that there? So again, here, if we look at this esterification reaction, we're going to put a box around our water, and that's going to come out. So once again, on the other side, we would have our water, and then we're just going to copy what's going on in this case. So we got CH3, C double bonded O. That takes care of everything to the left of my box. And now I'm going to connect it up here to the right of my box, and that's going to give me, again, my ester connection. And once again, nothing else changes as I do that. And that would be the proper way to draw it. Now, to name it, once again, we will dig into what we just talked about. And again, if it helps you, you can lay yourself up a line always between the carbon and the single bonded oxygen. And again, going towards the single bonded oxygen, that should be my alcohol part. So that is named as a group. So that is 2 carbons in this case. Or 3 if I actually looked at, I guess, at the alcohol that was there. So when we actually put the right number of carbons, that would be good. Kind of like 2, but 1 more makes 3. There we go. So that looks a little bit better. All right, so now in terms of our name here, we have 3 carbons on this side. So that's going to be a propyl group, right, based off of propane. And once again, coming this way towards the double bonded oxygen, that's your carboxylic acid. And that has 1 and 2, which again, based off of ethane, if you want to go all the way back there, and then just put O8 at the end of it and drop the E. And that's going to give you your propyl ethanoate. The other way is, this is technically that carboxylic acid, ethanoic acid. About the I. And you can then get rid of the IC at the end and just put 8 at the end of it and drop the acid as well. And that will give you your ethanoate. So whichever way you want to remember to do that. Again, the books, a lot of books will teach you to just take it out of the carboxylic acid name. Any questions on that there? All right, so let's draw this one here. Propanoic acid is going to be 3 carbons. So 1, 2, and 3. Again, it's going to be our carboxylic acid, as it is oic acid. We're going to do our H2O and our H3O. Methanol is an alcohol that has 1 carbon. And sometimes when you're drawing these things, it's helpful to arrange them like we did on some of the other ones, where you remember you got to take water out. So just arrange them so you can easily see, that water coming out. as opposed to maybe writing it like this, where you got to maybe kind of turn it around in your head and all that. So sometimes it's easier just to kind of turn it around, so everything is sort of arranged the way you're going to take out the water. So that's what we want to do in this esterification reaction. We're going to take out the water. And once again, that will give us our H2O. And now we're just going to draw exactly what's there. And I'm not going to lose a carbon, hopefully, this time. So we're going to just basically put all those guys together. And that would give me CH3, CH2, C double bond O, and OCH3. Again, there's our ester connection that occurs. And once again, in terms of naming, we will look right about here. Going towards the single bonded is our alcohol, which means there's a 1 carbon group, which means that is a methyl. Coming this way is our 3 carbon group, which is based off of propane. And once again, you could drop the E and put O8 at the end of it, and that would be propanoate. Or again, you could take the propanoic acid, drop the acid, drop the ic, and add 8 to it. And you could do that as well. So whichever way you want to remember it. So putting those together, again, group first. So that's going to be methyl propanoate in this case. Any questions on that there? All right. Perfect. So we kind of jumped the gun on it, but once again, you have the alkyl part that comes from the alcohol, and you got basically the carboxylic acid part, which is really the base of your name. And again, kind of ends in O8, however you want to put that O8 on there. So some esters do have common names. That's ethyl ethanoate. This is ethyl acetate because it comes from acetic acid, which is the carboxylic acid, which is also ethanoic acid. We're not going to really use common names too much for these guys, but you might still kind of see it. Methyl propionoate is the same as methyl propanate. Probably the only one that maybe we might use sort of the name here is ethyl benzoate. So if you happen to have a benzene ring attached there as your carboxylic acid, which is benzoic acid, we'll go with benzoate as the base of the name. And then obviously here's our alcohol part here, coming this way. 2 carbons gives you the ethyl part of it. So maybe that would probably be the only one, maybe common name that, you might use is the benzene ring. All right, so as talked about before, these things pop up in a lot of places. For example, aspirin, which is salicylic acid, is our ester. Here's our ester group there, right about there. And that's basically aspirin, which is basically synthesized from a carboxylic acid, which is this guy right here, and a alcohol, which is a carboxylic acid and an alcohol right here. So this is our alcohol and our carboxylic acid, and that is our water that's going to come out when it comes together. And it would be that type of deal right there. We're going to take that out when it comes together to make aspirin. We could also see some here. This is oil wintergreen, which I think is maybe one of the ones you might make this week. And that is used there to soothe skin, also as skin ointments. And again, here's our ester bond happening right about there in that particular case. All right, so why don't you name this ester? Why don't you also name this ester? Why don't you also draw? Let's do pentyl. Butanoate. And why don't you also draw butyl. Okay, let's take a look. So we'll start with the one that was on the paper. Once again, if we're going to name it, we hopefully should recognize the ester group right about there. And that means, again, if it's easier, just put a line right there between the carbon and the oxygen. And again, heading towards our oxygen single bonded is our alcohol part. So in that case, we were looking really at the group that is there. So that's a 2-carbon group, which means that should be a ethyl group that's happening. Heading the other way, away from that single bonded oxygen towards the double bonded oxygen is our carboxylic acid here. And in this case, it's 1, 2, and 3, which again is really based off of propane. And you could drop the E and put O8 at the end, or it's really propanoic acid, where you get rid of the acid and the IC and just put 8 at the end of it to keep the O. Whichever way you want to do it, but you should end up with ethyl propanoate. Yeah. Any questions on that particular one there? Looking at the next one, here's our ester group right there, carbon, oxygen, and another carbon on the other end. We'll see what I drew here. So it's just drawing squiggly lines. We'll still do the same thing there. We're going to go with our line between our carbon and oxygen single bond. Again, heading towards the single bonded oxygen is our alcohol part. And in this case, there's really only 1 carbon at the end, which means also has 3 hydrogens. And again, that should be a methyl on that end of it. Yeah. Heading the other way, obviously, with our double bonded carbon oxygen is our carboxylic acid. I actually drew the C there. So that's 1, that is 2, that is 3, that is 4, that is 5, that is 6, and that is 7 carbons, which is really based off of heptane. I'm personally just going to drop the E and put O8 at the end of it. So putting those together should give us like a methyl heptanoate in this case. Yeah. Any questions on that one there? Yeah. Once again, that is based off of heptanoic acid, right? And again, you could drop the IC in the acid and put 8 at the end of it if you want to do it that way. We're going to draw. So drawing, just like everything else that we draw, we're going to work backwards. So clearly here, we do see O8, which tells us it's an ester. And I would say probably in this one, much like maybe we did with the ethers, I would actually personally start with the functional group here. So I would start with what makes it the functional group, which is really our carbon oxygen double bond, and that's going to a single bonded oxygen. So when you're drawing these esters, I personally would kind of start with the middle part. That way, all you have left is just to kind of put the outer parts in. And we could do that really simply because we know the name here goes to the carboxylic acid part. And now that I have the functional group up there, I know my carboxylic acid part should be heading towards my double bonded oxygen, right? And that is what we're going to put there. You do need to be careful because I already have a carbon up there, so you got to count that one. So that's 1 carbon already up there. So butane is 4 carbons, which means heading to my double bonded side, which should be my carboxylic acid. Again, I need a total of 4 carbons at that point. Question on that there. That takes care of this part. Now I know that the group is really going to go to my alcohol part, which is where my single bonded oxygen is at, and pentyl is 5. That was a bad decision. Let's start that 1, 2, 3, 4, and 5. Now, just like everything else, it's just hydrogens, right, to fill it up. So we're going to do hydrogens 3 here. We need 2 there. We need 2 there. We need 2 there, 2 there. 2 there, 2 there, and 3 there. Yeah. Any questions on that? That obviously is the condensed formula. that I just drew. You obviously could do line structure, just draw the right amount of lines along the way. Same thing or same approach here for the guy on the bottom. That's O8, which tells us the carboxylic acid. And that is where I'm going to start with. So again, here, maybe we'll go right about there, try it. We'll start with this. Hexane means I need 6 total, again, heading to my double bonded side, which is where my carboxylic acid, I already got one. So that is 1, 2, 3, 4. Not so good. Let's try to squeeze it in there. All right, take 2. Get rid of some of this here. All right, we'll build some more room to do this in. All right, here we go. All right, so again, starting with the functional group here. And again, now I got 1 there, which means I need 5 more to give me 6 total. 5 and 6. So that's going to take care of the hexane part, and butyl is 4, which will go to my alcohol side. And now we'll just fill in our hydrogens in this case. Again, just to get carbon to 4 like normal here. Any questions on that one? I don't know what I was thinking. I was going to squeeze that in no matter what I did there. Question on how to draw, how to name. Again, on the drawing on this one, I would start with the center part and just work your way on the outside. So, all right. All right, so this guy here should then be, we look at this right there, that's going to be our alcohol part. So that is 1, 2, and 3, which again gives us a propyl. Coming this way is going to be our carboxylic acid part, which is 1 and 2. So that's going to be ethanoate. And again, putting those together should give us propyl ethanoate in this case. Yeah. So again, it's really important to understand which part's your alcohol part and which part is your carboxylic acid part. And again, kind of think about it as single bonded and double bonded. The way you can remember that is, right, carboxylic acid has the double bonded oxygen, right? So that should be the part where the acid part, the alcohol doesn't really have a double bonded and it just has a single bond. So that is, again, how you want to think about it. As we talked about, again, responsible for a lot of perfumes, aromas, like pineapple and oranges and all those good stuff. So here's a little table of all those things like pears, banana, oranges, pineapples. These are all our ester groups. And once again, we could break all these guys between the carbon oxygen single bond and always again towards the single bonded side is going to give us our alcohol group. So once again, that is our 3 carbon, which is our propyl ethanoate that we just saw. That's 1, 2, 3, 4, 5. So that's our pentyl ethanoate. That's a lot there, which is our 1, 2, 3, 4, 5, 6, 7, 8 octyl for octane, right? Basically, ethanoate, our ethyl, 1, 2, 3, 4 butanoate, and our 1, 2, 3, 4, 5 pentyl, 1, 2, 3, 4 butanoate, again, responsible for it. All right, draw a couple of these guys, condensed ones of 3 bromo butanoic acid, ethyl propanoate. Okay, so let's take a look. First one is oic acid, which once again should tell us it is a carboxylic acid, not an ester. So That is the functional group that we're dealing with there based on the oic acid. So we'll do like normal here. We got butane basically, which is our 4 carbons. Since we know that this is the functional group, it has to go on one end or the other. You need to put it on one end. That will take care of basically that part of the name. Once again, this has to be carbon number 1 in this case, which means that carbon number 3, which is right around here, we should have a bromine hanging out. And now we're just down to hydrogens to fill into 4. Needs 1 and needs 3 in this case. Again, if you were to draw more of a line structure there, something like this. Any questions on that one there? Here we see O8, which tells us it's an ester, and again, looks very similar to our carboxylic acid because it's made from a carboxylic acid pretty much. So again, on this one, we're going to actually start with that functional group, and then we're going to fill in what we need on either side of it. The propane part here tells us it's 3 carbons, and that should be our carboxylic acid side, which is our carbon-oxygen double bond side. So we already have 1 carbon there, so that's 2, and then that is 3, so that takes care of all that. Our ethyl comes from our alcohol side, which is our single bonded oxygen side, and ethyl is 2 carbons, so 1 and 2. And now we're just going to fill in some hydrogens here. Any questions on that one there? And again, if you wanted to do a little line structure there, it looks something like that, perhaps. There's our 1 carbon, 2 carbon, 3 carbons with our double bond, our oxygen, and then our 2 carbons, carbon and carbon. Yes. Other questions or questions on that there? All right, so obviously you need to be able to draw esters, the esterification reaction, be able to name them, and obviously still carboxylic acids. So let's talk a little bit about a hydrolysis reactions that esters undergo. Esterification is basically kind of like a dehydration reaction, if you want to think about it that way. You take water out to make it, right? So we take the water out between the carboxylic acid and the alcohol, and then we squeeze them together. So hydrolysis is basically kind of like the reverse reaction where you're going to put water in. So hydrolysis means, again, water is usually involved some fashion. And if you remember, to make it, we take water out. So kind of will make sense. In one case, putting water back in will break it back apart. By the way, when we do this, we're going to break it back apart the exact same place where we put it together, right? So that's where we slide it together. And if we have to take it apart, we're going to take it apart in the exact same spot that we pushed it together in. So there's 2 types of hydrolysis reactions. One is an acid hydrolysis and one's a base hydrolysis. The acid hydrolysis of a ester will basically get you back everything just like you started. So it'll get you back the carboxylic acid just like it was, and it'll get you back the alcohol like it was. So if you do the acid hydrolysis, so here we have water, and H plus here means acid. So sometimes we'll just put H plus up on top of the arrow, and that indicates an acid as being used. They also may use a little delta symbol there for heat as well, a little triangle sort of symbol. So once again, what's going to happen is when we look at this guy, we're really just going to take it apart exactly the same way that we put it together. And the water will come on just like we take it off, basically. So we can kind of, again, think of water as kind of 2 parts. We could think of water as H and OH. So those are kind of the 2 parts that could come on. So if you were going to draw this reaction here, and this is an acid hydrolysis, the first thing that you would want to do is what we just talked about. I know I'm going to break it apart, so I got to break it apart pretty much where I put it together. And what that means is you essentially should just draw exactly what you have there, except just separate them where you drew the line. So you're just going to separate them out. So nothing will change on the left. So you'll have this. And that's where I separated it. And then on the right, we have basically this. So I just basically pull them apart. So again, put them together, we push them together. And when we add water and acid hydrolysis, we're just going to push them apart. So what is left is what you should know in this case is you should actually get the carboxylic acid back and you should get the alcohol back. So that's essentially all we have to do is use water to build that. So in order to get the alcohol back, we just need an H. So this guy's going to end up over here and we're just going to put the H on it. To get the carboxylic acid back, we need an OH, which is good because that water has an OH left over. So that is where that is going to end up over here. So we're going to use our water to basically rebuild back the carboxylic acid and the alcohol. And you could think of this reaction, which is referred to as the acid hydrolysis of an ester, as really just the opposite of putting it together. So esterification, take water out and push them together. Acid hydrolysis, put water back in and separate them back out. So they're really kind of reverse reactions of each other, the esterification and this reaction. Any question on that one there? Now, there's also another type of hydrolysis reaction that occurs with an ester, and that is a base hydrolysis. And that is sometimes referred to as a saponification reaction. Saponification means soap, basically. So this is kind of the reaction of how you make soap, essentially. So this is basically like making soap. So if we take our ester, we're going to still break it apart in the exact same spot. The difference here, though, is it's a base. So we're going to use a strong base like we have here. Sodium hydroxide is a strong base and a little bit of heat. So if you think about the acid one that we just did, we had water involved, right? And here we don't necessarily have water per se, but we do have a part of water. We have the OH part of water, but we don't have the extra hydrogen that we did with the acid part. So what we end up with is a little bit different than what we got on the previous one, but you should still approach it the same way, which means you should still take this guy and go, I'm going to break it apart right where I put it together. You should still draw the two parts and separate them out. And now when we think about what we got to do in this case is we have basically Na, O, and H in this case. So if we just kind of keep track of stuff, the one thing that we will get back in this case for sure is the alcohol. So the alcohol will be made back just like we had it. So that's going to, from our sodium hydroxide, that's going to frankly use up our H there. And we're going to use that H to get our alcohol back. At this point, we don't really have the OH that's necessary to regenerate the carboxylic acid completely. But what we have left is an oxygen that now has a negative charge because that H is like positively charged. And we will end up with an oxygen and a minus and an Na plus. We will actually result in a carboxylic acid salt. So what we were looking at earlier, we'll actually get a salt rather than the completed carboxylic acid because we're using a base rather than water and an acid in this particular case. That acid is necessary to keep the hydrogen on to make the carboxylic acid part, the OH part. In a basic conditions, that H will not want to stay with the OH there and make the carboxylic acid group. So very similar, except that we get a salt rather than the carboxylic acid. And it's really more so because of the conditions of basic. because that acid will then basically donate its proton over and it will stay on basically. And that's why you end up with the salt rather than the carboxylic acid in this case. So if you remember earlier, we made the salt and sort of our hydronium ion, our H3O plus. That is essentially what is happening in this case. This is also really how soap is made. Soap is really a really long chain. I'm not going to draw all the hydrogens, but all these carbons have hydrogens, like 18 of them or more. It's really what is sometimes referred to as a fatty acid. So what you end up with is this nonpolar part of soap, which is sometimes referred to as a nonpolar tail. It's all the carbons and hydrogens basically in here. All right, I'll go back and scribble in some hydrogens all the way across here. So forth. And then we have the polar head of soap. And this is a reaction that we use with fatty acids. Fatty acids are long chain carbons that have the carboxylic acid group at the end. And this will produce basically soap. And that's important for how soap works because dirt, again, is nonpolar usually. So because soap has basically two sides, a polar side and a nonpolar side, the nonpolar side, which if I draw a kind of like line structure, kind of all the carbons and hydrogens, will basically surround all the dirt and grime because nonpolar and nonpolar will mix, right? Same intermolecular forces, so they will actually mix together. And what that will leave on the outside, I'll just draw it here on one or two of these guys, is the polar head, which is on the outside. So what happens when you use soap is it traps all the dirt on the inside, was referred to as a micelle. On the outside, all the soap lines themselves up with the carboxylic acid part on the outside, which is polar. And that's really good because after you use soap, you usually wash it off with water. And water is polar, right? So hopefully. So water is polar and the outside there, soap is polar. So when you wash it with your polar water, out goes the soap that has basically your dirt trapped on the non-polar side inside and you feel clean. It's good to know how soap works, I suppose. That's any questions on that there? All right. So we'll talk a little bit more about that later on as well in a later chapter, I think. Why don't you write the reaction that you should get here when you start with methyl. Okay, let's take a look. So I scratched out methyl acetate, which is sort of the common name. And again, that comes from acetic acid. So that's ethanoic acid. So we're going to draw methyl ethanoate. And again, we see the O8, which tells us it's an ester. So we'll start with that part here. And once again, ethane means two carbons on our carboxylic acid side, which is our double bonded side. I already have one, so I just need one more. And methyl is one carbon there on my alcohol side, so we'll do that. And we will do this right there. We're going to do the hydrolysis here with water and an acid catalyst. And because it's an acid catalyst and water, we know that this is basically the reverse of the esterification reaction, which means we actually get back both parts in their completed form. So here again, we just want to start with separating this out where it comes together. So that is one part I'm going to draw, and then I'm going to separate it out and draw my other part. So again, this is my carboxylic acid part. This is really my alcohol part here. Now what's left in this case, since we do get both parts back completed, in order to get this guy back to a carboxylic acid, I need an OH. So that is where that is going to end up. And to get the other guy back to an alcohol, I need an H. So that is where that guy is going to end up. And now again, I get my carboxylic acid and my alcohol back. Once again, you can think of the acid hydrolysis as kind of the reverse of the esterification reaction. And you get back your two original guys. Any question on that one there? On the bottom one, we're doing the base hydrolysis, which is, again, a little bit different. In this case, we are starting with the exact same ester to begin with. And that means, in this case, we're going to add KOH And again, this is sort of how it's going to add. We got this guy, which is kind of negative oxygen, and this guy, which is like the positive hydrogen, is sort of how that's going to come together. Again, in this case, because we really don't have water and the acid, and because of the basic conditions, is not going to allow you to really retrieve the carboxylic acid. Because what's going to happen with the carboxylic acid is in that basic conditions with potassium hydroxide, this guy's going to want to come off. So that's why you can't really keep it and get back the carboxylic acid. It's going to want to donate his proton and do an acid-base reaction because it's really basic conditions. So that's really the reason why we don't get the carboxylic acid back in that case, because of that. So we do still get the alcohol back in this case. So once again, we're just going to break it apart in the exact same location. We're going to start with this. And we're also going to get this guy, which again is our alcohol part, which we should get back. And this is really our carboxylic acid part, which we're not going to get back. So to start with, what we could get back pretty easily is that's going to get us back to our alcohol by adding the hydrogen there. So we'll pop our hydrogen here. And once again, once we get rid of that, we really have a negatively charged oxygen, which we know does need to go here, right? Because that's kind of like what a carboxylic acid looks like. It will have a negative charge, and in this case, it will have a positive charge from our potassium, and we will make our carboxylic acid salt. So again, in that basic conditions, really because of the basic conditions, there's no way to keep that sort of acid, carboxylic acid, still protonated. The hydrogen will want to come off, so you'll get the carboxylic acid salt rather than the carboxylic acid completed. Any question on the hydrolysis reactions here? Okay. I think that's what those pictures show, so that's good. In that case. All right. We're down to 2 organic groups to go, and now we're going to get into some nitrogen-containing groups. So these are amines. These are nitrogen-containing groups. And basically, amines are pretty much derivatives of ammonia. So they basically have a functional group of a nitrogen and 2 hydrogens. They basically come from ammonia. If you remember, ammonia looks like this. So they're derivatives of ammonia, and this is really the functional group here, that NH2 group that is present. Because they are derivatives of ammonia and they have that nitrogen and hydrogen, they can hydrogen bond like, water and stuff like that, because that is what you need for hydrogen bonding, which is a hydrogen attached to a nitrogen, oxygen, or fluorine. So they can do some participation in hydrogen bonding, which makes some of them soluble in water and be able to behave similar in some certain fashions to other organic molecules. So amines, again, are derivatives of ammonia, in which one of the hydrogens are basically replaced by a carbon-containing group. So these are our amines here. We have our nitrogen, and again, some carbons there. We have our nitrogen and a couple of carbons, and we have our nitrogen and our hydrogens in this case. So we can also classify we can classify amines the same way as we classify carbons, and as primary, secondary, and tertiary amines. Works the same way. It's basically, in this case, how many carbons are directly attached to the nitrogen. So in this case, we want to look at how many carbons are attached to nitrogen. In this case, this nitrogen is attached to 1, 2, and 3. This is a tertiary amine. This nitrogen is attached to 1 and 2, which is a secondary amine. And this nitrogen is attached to only 1 carbon right there on the ring, and that would be a primary. Once again, much like how we do carbons and all that, you could also look at hydrogens, which is how some people will classify them based on the number of hydrogens that are there. So 2 hydrogens would mean a primary. 1 hydrogen would mean a secondary, and no hydrogens would be a tertiary. Once again, I think it's just easier to look at how many carbons are directly attached and just count the carbons, and that gives you the actual number of what the primary, secondary, tertiary would be. And that's what we see here. Primary amine has one carbon group directly attached to the nitrogen, secondary 2, and tertiary 3. So once again, there's our 1 carbon attached, 2 carbons attached, and 3 carbons attached directly to the nitrogen, giving us a primary, secondary, or tertiary amine. Any questions on that there? So how do we name some of these? We can name them. One way is a common way, which is sort of what it looks like we will do for our amines, is more of a common way of naming it. And much like what we did with our ethers, where we kind of went to the oxygen and figured out what groups are on the sides of it, we would do the same thing here. We could go to the nitrogen and figure out what groups are there. So for example, we go to our nitrogen, the only group attached there is a 1 carbon group, which is a methyl, and then we just put amine at the end, so that is methylamine. Here we go to the nitrogen, and we have 1 methyl group there and another methyl group there, which gives us 2 methyl groups. So that gives us dimethyl, and again, just put amine at the end. And lastly, 1, 2, and 3 methyl groups in this case. So 3 methyls would be trimethyl. And once again, just put amine at the end. So one way that you can name these is basically more of a common way of naming, and we'll go with that for amines here. Basically just figure out what groups are directly attached to the nitrogen and basically just put them in obviously alphabetical order if they're different groups that are attached. So, if you had like a ethyl methyl amine, so you go alphabetical like normal with the groups if there happen to be different ones attached. Question on that there. So that's what we see here. We just name it as the alkyl group and put amine at the end. And again, there's our ethylamine, which has 2 carbons here. That's our ethyl group. This is again our dimethyl, as we have 2 of those guys attached. And again, as I mentioned before, we will go in alphabetical order. So that is an ethyl group. That is a methyl and a methyl. So those together gives us our dimethyl. And just like before, we're not going to look at the prefix. So it is E before M here. So we're not looking at the di like we did previously as well. So that is why it's ethyl dimethylamine. That guy on the bottom there would be a tertiary amine. The guy in the middle would be a secondary amine. And the guy at the top would be a primary amine. Questions on there? All right, write the common name for each of these and decide, is it a primary, secondary, or tertiary? Okay, so let's take a look at the classifications first. So much like what we do with carbons, here though, we are going to focus in on the nitrogen to help us classify it. And it is how many carbons are directly attached to it. In this case, looks like just 1. And that would give us a primary amine in this case. Here, looking at this nitrogen directly attached is 1, 2, and 3, which would give us a tertiary amine in this case. Any questions on that there? To name it, we will roll with the common name, which means we just really want to look at the nitrogen and see any type of carbon groups that are attached directly to it. In this case of the first one, this is the only carbon group that's attached, and that is a 3 carbon group, which is a propyl. And then we just will call it propyl and then put amine at the end of it. So that would be that one. Here we have 1 carbon group here, which is a methyl group. We have another 1 carbon group here, which is a methyl group. And attached over here is a 2 carbon group, which is an ethyl. Once again, these 2 guys will become a dimethyl. And again, alphabetical E before M in this case. So this again would be our ethyl dimethyl amine in this case. question on any of those names there. All right, let us lay it up